Hi, you guys. I'm back with another video, and I'm actually filming 2 days in a row, although I'm not going to be posting it 2 days in a row. I am going to DC this weekend, and that's usually when I like film on weekends. So I'm hoping to actually do like a bunch of videos on work nights and then slowly roll it out over the next couple of weeks. So let's hope I continue to be as consistent as I have yesterday and today. All right, so let's get started with this problem. Some sliding rocks approach the base of a hill with a speed of 12 meters per second. The hill rises at 36 degrees above the horizontal and has coefficients of kinetic friction and static friction of 0.45 and 0.65, respectively, with these rocks. Find the acceleration of the rocks as they slide up the hill. My voice just cracked. Sorry. B, although I'm not going to include it in this video, but B, once a rock reaches its highest point, will it stay there or slide down the hill? If it stays, show why. If it slides, find its acceleration on the way down. Okay, I love, 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 love this problem. It was so much fun to do, and you're about to see why. It's such like an elegant solution. So let's get started on that. So first, just to get a better idea, you guys know that I really like to draw out my problems first. So let's just draw a green grassy hill. Okay, so this can be our green grassy hill. Okay, and you know what? Actually, no, we're gonna do a little bit better. I'm gonna make it a little bit more. There we go. Okay, a little bit more exaggerated. All right, so we know that there are some sliding rocks that are approaching the base of this hill. So, the base of this hill is like this dotted line that I just drew. And if there is a rock, that's gonna be the rock. And it is approaching with a speed of 12 meters per second. And the hill rises up at 36 degrees above the horizontal. And we know that the coefficients of kinetic friction are 0.45 and static friction is 0.65. Okay, so what we want to do is find the acceleration of the rocks as they slide up the hill. So, okay, I guess there's like multiple rocks where just all three of them are moving together, apparently. I don't know why they do that, but let's just say they are. Okay. All right, so now we gotta write down all of our knowns, right? So I'm just gonna, again, start with A. And pretty much our knowns are just these three things, right? So we know that mu k is equal to 0.45, mu s is equal to 0.65, and then v is equal to 12 meters per second. Okay, so what we want to do is we want to find the acceleration of the rocks as they slide up the hill. Okay, so let's pause here for a second. So you might be thinking, hey, I thought this is a forces unit, so why are we trying to find the acceleration? Well, great question. Force and acceleration are very closely related to each other. How are they closely related to each other, you might ask? Well, we know that force is actually just mass times acceleration, right? So if we want to find out the acceleration, we have to find the force first. And how do we find the force? Well, let's actually draw a force body diagram of these rocks sort of approaching the hill, on their way up, not approaching the hill, but sort of on their way up on this hill. And then when we have our force body diagram, we'll know all the forces that are sort of acting on these rocks. And then we can figure out what the acceleration is because we'll know what forces or what force is acting on it, right? Okay. Or forces are acting on it. You'll see in a second. Okay. So instead of drawing, actually, no, let's just draw this as like a circle. It's not going to kill us. Okay. or not a circle, but like rock shaped. Okay, so now for the fun part. What are the forces on this rock? Okay, so obviously, force of gravity, right? Because let's just assume I mean, regardless, if we're on Earth, if we're on any type of planet, there's going to be some force of gravity, right? Okay, so then what else, right? So we know that I'm going to draw this in a different color. I'm going to draw this in black, actually. So we know that this is like the direction of movement, right? Of the rock. So if that's the direction of movement of the rock, then here's a hint, we have friction that's working in the opposite direction, right? Because friction always opposes. Sorry, I just burped. I'm sorry. Okay. I don't know if you heard that. So we have friction that's working in the opposite direction. And that is, so how do we know which friction it is? Well, when an object is moving, then we have kinetic friction working on it, right? Well, I'm not going to say working on it, acting on it, right? I always say working, but I should be saying acting. So we have kinetic friction acting on it, right? And so we have K over here. But if the rock were to be just in place, then we have static friction working on it, right? Acting on it, not working on it, acting on it. Okay. So what else? What other forces do we have? We also have the normal force. Now, this is a little bit of a tricky concept, okay? And I'm not even going to try to justify or explain it, but you can do more research about that later. Or you can leave it in the comments and maybe I'll do a video about it if I have time. But we have normal force. And normal force always acts um, in the direction that is perpendicular to the surface that the object is touching, right? So what does that mean? That means that normal force is going to be this way, right? Because this is the direction, sorry, this is the surface that the rock is touching. So normal force is the opposite direction, right? So we're gonna call that Fn, normal force, right? All right. So now also what we want to do is we want to define some type of coordinate system, right? And with a ramp, I'm not going to explain why this is, but it's in your best interest when you have ramp problems to set up your coordinate system sort of like this. Okay? You can solve it this way, but what ends up really happening is you end up with so many different components, right? Because yes, FG is like um, in like a negative y direction, but then you have to work with this component and this component and this component and this component, right? So then because it just gets like complicated, it's so much easier to just remember that coordinate system can be defined as anything. So you can just set it up the way that you want. So we just set it up like this over here, just the way that I showed it. And that way, all you really have to do is break this into components, right? So it's just less work for us. So that's why we like to do it that way. Okay. Now what? So now we are, yeah, yeah, that's it. That's our diagram. Okay, I am gonna do one more thing. I'm gonna just go ahead and break FG down into its components, right? So that we can use, I'm gonna break it down into like this X and Y component, right? So if we say like, this is plus X. Oh, sorry. I don't know why I did that. Okay. Okay. So if we say that this is plus X and this is plus Y, we want to be able to break it down into its components, right? So basically, this is going to be one component, right? And then this is going to be one component, right? And we can use similar triangles to figure out that basically this is 36 degrees, right? And how do we actually know that? Because if we were to extend this, we know that this is going to be all angles of a triangle. Well, actually, no. Yeah, I mean, you can say it two ways. this plus this has to equal to 90, right? Then that means that this plus this has to equal to 90. So then that's how we know that this angle right over here is 36. Okay, 36 degrees. Awesome. Okay. So now what? Okay, so now that we've already broken it down and we have our diagram, remember that how we're going to solve this problem is by solving for the forces that are acting on it, right? So how do we do that? Well, let's go back to we have to come up with equations, right? So we have to come up with equations that describe this system. And we can do that by writing down x and y equations, all the forces acting in the x direction and all the forces acting in the y direction. So what do we know? We know that um, all of the forces acting in the x direction, right, are going to be just some force F. And some force F is just going to be mass times acceleration, right? And that's how we're going to solve for acceleration. Because remember, the rock is accelerating in this x direction, right? Whether it be negative x or positive x. How do we know that? Because it's changing speed, right? And then we know that the y direction is going to be 0. How do we know that it's 0? Because this rock isn't really experiencing any motion in the y direction, up or down, right? But the x direction, it is. Okay, so now what we have to do is we have to describe, we have to actually write out these equations, right? So we have to, if we write down all of the forces in the x direction and the y direction, then we can just solve for this, right? So let's go ahead and do that. Okay. All of the forces in the x direction, what do we have? Well, we have positive force of friction is going in the positive x direction. So we have positive force of friction, kinetic friction. And what else do we have? We also have this positive force component of gravity. And what's that component? It's Fg sine 36, right? Plus Fg sine 36. And as we said, that is equal to mass times acceleration. All right, so now let's do the same thing in the y direction. And in the y direction, we have our normal force, which is just up, positive, right? So Fn minus, now we have this negative gravity, right? This negative component of gravity. So minus Fg cos 36. And that's equal to 0, just like we said. All right, cool. Now, all we have to do is solve for this. So let's start with this equation over here, right? Basically, what we figured out is Fn is equal to Fg cos 36. Cool. All right. And let's just label this as, well, let's call this 1, let's call this 2, let's call this 3. Now we can, okay, so now let's go ahead and solve, let's simplify, solve 1, okay? What is Fk? Fk can be written as Fn mu k, right? And we actually, so I'm going to write that down. So Fn mu k plus Fg sine 36 is equal to ma. All right, well, we know what Fn is, right? Fn is Fg cos 36. So let's write that down, right? So we have Fg cos 36 times mu k plus Fg sine 36 is equal to ma, right? Well, now we can simplify this further. Fg, as we know, is just equal to mg, mass times gravity, right? Mass times acceleration due to gravity. So we're going to do mg cos. Actually, even before that, another thing we can do that's going to make our lives so much easier is we can just factor out fg, right? So let's factor out fg. Okay, mu k cos 36 plus, oh, I have to write that. Mu k cos 36 plus sine 36 is equal to ma, right? And as we said, fg is just equal to mg mu k cos 36 plus sine 36 is equal to ma. Well, we can cancel out m and m, right? So then acceleration is just equal to g mu k cos 36 plus sine 36, right? And then acceleration, we can just plug these values into our calculator because we know that, we have mu k over here. We know that g is equal to 9.8 meters per second squared as per always on planet Earth. Um, well, take that with a grain of salt, if you know what I mean. Gravity does kind of vary different locations on planet Earth, but just for sake of simplicity, it's 9.8. Um, and then cos 36 sine 36, we can just plug that into a calculator. So let me do that right now just to double check my solution. So mu k 0.45 times cos 36 plus sine 36 times 9.8. And I'm getting that the acceleration of the rock is 9.33 meters per second squared. So that is our solution. Find the acceleration. The acceleration is 9.3 meters per second squared. All right, thank you so much for watching, and please don't forget to like and subscribe and share with your friends. See you next time.